Good morning, students. My name is Dr. Srinath. I will be explaining laser diffraction experiment. So the goal of this experiment is to use diffraction of laser light to estimate the wavelength of the laser. So as you know, when light passes around a corner, it bends. So when laser passes through an optical device known as diffraction grating, diffraction grating consists of a transparent sheet with a lot of parallel lines on it. And when the laser light passes through this diffraction grating, the light gets split into various components, and each of them spreads out of the other side of the grating, and those light rays interfere among each other to form a nice diffraction pattern. So we will use the properties of diffraction grating to estimate the wavelength of laser. So this will be the goal of the experiment. To do this experiment, you basically need three components. First of all, you need the laser. This is a helium neon laser, which is red in color. Then you need a diffraction grating, which is mounted on a particular mount. So this is diffraction grating. So as I told you, diffraction grating is an optical element with many parallel lines drawn on it. As you can see, it is written that laser grating 500 LPI. 500 LPI refers to the fact that there are 500 lines per inch of the grating. So that there are that many lines which act as obstacles on the path of the laser, and the laser diffracts out of this grating. And then finally, to observe the diffraction pattern, you have a screen, and I have put a graph paper on top of the screen to measure the location of the fringes. So first of all, let me illustrate how the laser, let me switch on the laser. A word of caution: so when you are performing this experiment, make sure that the screen is in position before turning on the laser. So there is a switch at the back of the laser. There is a switch at the back of the laser. If I turn this on, you can see that a red spot appears on the screen. So ensure that the screen is in place before turning on this laser, so that the laser doesn't fall on someone else's eye. Also, you are never supposed to look at the laser with your eye. It will damage your vision. So the basic idea is that when the light ray passes through this grating, you can see that it passes through the grating. You can see that diffraction pattern with central maxima and various other order maxima are created on the screen. So this is the basic idea. So what we will do is we will measure the location of each maxima, measure the distance from the grating to the screen, and then use the formula that we have discussed to derive the wavelength of light. So let me get into the details of how we perform this experiment. The first step to performing this experiment is to note that the laser light from the laser falls on the screen. So you see that there is a bright red spot on the screen, and you have to mark the position of the screen with a pencil. So you put the pencil on the dot and make sure that you make this dot. Okay. Then you have to place the grating at a suitable distance from the screen. So in fact, to measure to make this experiment convenient, to perform this experiment in a convenient manner, we have mounted this on an optical bench, which consists of this rod in which there is a scale which has been marked. So this screen has been mounted at the zero location. The laser is at the other extreme end, and the grating is in between the laser and the screen. So in principle, you can actually move this grating to and fro. You can choose the position of the grating, and what you can do is you can position the grating in such a way that this grating is, say, 90 centimeter away from the laser. So if you look closely, you will see that there are fine markings on this optical bench, which tells you that this grating has been kept at 90 centimeter away from this screen. So So what we will do is we will perform this measurement at different distances from the screen. At this time we will do it 90, then we will move it to 100 and then 110 centimeters. Having placed this grating at the required distance from the screen, and now we need to raise the position of the grating. So you can you can move the grating up and down so that the laser light which is coming from this laser will pass through the grating and then fall on the screen. So in order to do that, you have to lift this grating, and when you see that the laser light is passing through the grating, you have to clamp the grating. Okay. However, you notice that even though this grating has been clamped, it is true that the light is passing through the grating. However, the position of the grating is not such that it is not perpendicular to the direction of the laser. For this, we need to do another adjustment. So what you have to do is, so there is a laser light which is passing through the screen, so through the grating. Now you have to adjust the position of the grating. You have to tilt it such that so when the laser light passes through the grating, a part of it is transmitted and a part is reflected. So you have to ensure that the reflected part, which is you can see here, is reflected back to the laser. So you have to turn the grating in such a way that the reflected portion passes directly into the laser. It goes directly into the laser. So once you do that, then you can tighten this clamp such that you can tighten this clamp. So this will ensure that the laser light is perpendicular to the direction of the. It will ensure that the laser light is passing perpendicular to the grating. Let me refine this adjustment. Now I have positioned this grating in such a way that the reflected portion of the laser light, which is bouncing from this grating, falls directly into this laser. This ensures that the laser light is perpendicular to the plane of the grating. So this completes our setup of the arrangement. And as you can see, the light which is passing through the grating makes a nice diffraction pattern on the screen. Now what you have to do is mark the position of different orders of fringes on the screen. So you should ensure that when all the setup is done, the central maxima falls on the exact position where we had marked. So if you look at this, you can see that there is a pencil marking here, which is where the central maxima is. Then on to the either side you have the first order maxima, second order maxima, third order maxima, fourth order maxima, and so on. And to the left also you have first, second, third and fourth order maxima. So what you have to do is you have to mark the position of these maxima. Similarly to the other side. From this marking, you can now take out the graph sheet and you know what are the positions of the central maximum, first order maximum, second order maximum, and so on. So this gives you the distance of the fringe from the central maximum. You also know the distance of the grating from the screen. With these two distances, you can measure the angle at which each of the diffraction fringes has been formed. Once you know the angle, you can use the formula d sin theta m is equal to m lambda, where m refers to the order of the fringe. You can compute, you know what is the distance, you know what is little d. D refers to the lines per unit length of the grating. You can use that information along with the information about the angle and the order of the fringe, and you can draw a graph between sin theta, which is sin theta m versus m. So sin theta m is the sine of the angle at which a particular fringe has been formed, and as you can see, the certain graph will be a straight line, and from that graph you can compute the slope, which will give you the wavelength. So the theory is already explained in an earlier video, and if you have questions, you should refer back to that video, and I will provide the data from this experiment, and you should analyze this data using the theory, draw the graphs, and estimate the wavelength of the light. I hope you learned about diffraction grating and you found this experiment interesting. Thank you.